In this lesson, we will study partial derivatives for functions of two variables. Recall the limit definition of the derivative given on the panel to the right. The essence of this definition is that we find the slope of lines secant to a function f, and by evaluating the appropriate limit, these slopes will give the slope of the tangent line. That is, for a point A in the domain of f, the value of f prime of A gives the slope of the tangent line at x equals A. Combining this with the point on the curve, we can find the equation of the tangent line at x equals A. Now that we are working with functions of two variables, we must reconsider the notion of derivative. Consider the definition of partial derivatives shown on the panel to the right of the graph. Several things should be immediately clear. For one, we have two different notions of partial derivatives, one for each input variable of the function. The topmost limit, denoted by f with the subscript of x, is referred to as the partial derivative of f with respect to x. The other limit is the partial derivative of f with respect to y, and is denoted by f with the subscript of y. Notice also that the definitions presented are very similar to that of f prime in the one variable case. We will see that they have similar interpretations as slopes of tangent lines in a moment. Before we go on to the visuals, we also note that just as the derivative of a single variable function can be noted as f prime or df dx, partial derivatives have an alternate notation given at the bottom of the panel on the right. Note that delta is used in place of d to distinguish a partial derivative from a single variable derivative. In this format, partials are sometimes referred to as del f del x or del f del y for brevity. A key observation to understanding the geometric interpretation of the partial derivative is that in each partial, the limit only involves one variable. For instance, in the partial derivative with respect to x, you may notice that the limit only involves x, and thus the y value is fixed. Hence, when performing calculations, the y value is typically treated as you would a constant. Consider the function shown. We will first examine the partial with respect to x at the point 2, 1. When considering the partial with respect to x, the y input variable is fixed at y equals 1. Thus, we only need the slice or cross-section of this graph, where y is 1. When we look at the intersection of the plane, y equals 1 with the graph of our function, we are left with a 2D path. For clarity, we can also display this cross-section on a 2D xz plane. When computing the partial derivative with respect to x at 2, 1, you take the curve shown, which is formed by the intersection of the surface with y equals 1. And find the slope of the tangent line to the curve at x equals 2. Let us now consider the partial with respect to y at the same point, 2, 1. When considering the partial with respect to y, the x value is fixed at x equals 2. Thus, we consider the intersection of our surface with the plane x equals 2. This creates a different path, which is displayed on the right-hand panel. To calculate the partial derivative with respect to y at 2, 1, you will examine the curve formed by the intersection of the surface with x equals 2, and find the slope of the tangent line to the curve at y equals 1. For our last example, we will examine the paraboloid given by the equation f equals negative x squared minus y squared over 2 plus 4, and the partial derivatives at the point negative 1, 2. By treating y as a constant, we see the partial with respect to x is negative 2x. Likewise, treating x as a constant, the partial with respect to y is negative y. So at the point negative 1, 2, the partial with respect to x is 2, and the partial with respect to y is negative 2. Now let's examine what this tells us geometrically. For the partial with respect to x, y is fixed at 2, so we look at a particular slice of the function. The partial derivative tells us the line tangent to this curve, lying in the plane y equals 2 at the point x equals negative 1, has a slope of 2. Now for the partial derivative with respect to y. X is fixed at negative 1, so we examine the cross-section of the function parallel to the yz plane where x equals negative 1. At the point negative 1, 2, the partial derivative with respect to y is negative 2, which tells us that the slope of the tangent line to the curve here is negative 2. In this graph, you can examine both slices and the corresponding tangent lines. This completes the lesson on first partial derivatives. You can look down to go to the main menu and select another lesson or demonstration.